The next few slides are going to be talking about petroleum, how we take crude oil and make it into usable or separate it into usable formats, what changes we can do to that particular fuel, and then also what octane ratings mean at the gas station. So whenever a manufacturer gets in crude oil, it contains hundreds and hundreds of different hydrocarbons. Each of those hydrocarbons have what we call a different volatility. That's a good word to learn there. Volatility, almost lost my pen. Volatility is just how easy it goes to a gas phase. So if it's really small, it's going to have higher volatility. It's easier to go to a gas phase. Or if it has certain structures, as we're going to learn about, like a ring structure is more volatile than an unbranched chain. So we want to take all of these different hydrocarbons that we get and we want to refine them, meaning we want to try to change some of them into usable gasoline. We're looking at gasoline in particular for this particular chapter. And the first thing we have to do is we have to separate the different links or the different forms of volatility that we have. And the way that we separate them is based on their boiling points. So that's the temperature at which it turns to a gas, the temperature at which it turns to a gas. And the method that we're going to use is called fractional distillation. So let's see what that looks like. Okay, so this is supposed to represent a fractionating tower. And again, what we're trying to do is we're trying to pull apart or separate the different components in all of these different hydrocarbons based on their boiling points. So the crude oil starts off down here at the very, very bottom, and we're going to heat it up. So it goes through this furnace and it starts heating up. Now, once it's heated up, it goes to this tower. And we're going to see how long does it take or what temperature can it drop to before it actually changes back to a liquid. So the stuff at the very, very top, these are things that are going to be very, very volatile. And again, volatile just means that it likes to be a gas. And then the things at the very, very bottom don't like to become a gas. In fact, some things aren't actually going to vaporize. Some things are going to stay kind of a liquidy substance. And so that's the residue that comes off the bottom, such as asphalt and tar. That's what we're going to use that fraction for. If you can raise, so you've heated it up, it's going to stay a gas just a little bit, and then it starts to liquefy. So we're going to pull that fraction off, and that might be used for lubricating oil or paraffin wax. The next section could be used for diesel, for furnace fuel, heating oil. The next section is for kerosene and jet fuel. And then this part, we're cooling it off a lot more before it actually changes back to a liquid. So this had a much lower boiling point. It is much more volatile than some of the things below it. This can be your straight run gasoline. It can also be used for feedstock or your beginning products for a lot of plastic, chemicals, and textiles. At the very, very top are the things that never quite change back to a liquid. We're just going to take those gases and we're going to collect them. So in each of these fractions, there's still a wide variety of different compounds. We're not just simplifying it or isolating one compound. We're taking a group of compounds that all happen to boil at about the same temperature, and we're pulling those off all at the same time. Now, the next thing that we can do is we can take that section of compounds that came off with the same boiling point, and we can do alterations on the compound itself. Now, when we start altering the compounds themselves, the cost is going to go up. But let's say you have a really, really long hydrocarbon molecule and you want two shorter ones instead. Well, you can do something called catalytic cracking. So catalytic means that it uses a catalyst. A catalyst is something that's going to generally speed up a reaction, or it changes the pathway of the reaction, but it can be reused over and over again. So it's not actually part of the reaction. And cracking refers to the idea that we're going to take something large and we're going to crack it into smaller pieces. So we break apart a large molecule with the use of a catalyst. Now down here, what this is trying to show is that it starts with C12. That means that it's a hydrocarbon chain with 12 carbons in a line, and you can notice they kind of zigzag back and forth because that's what carbons like to do in real life. And what we're going to do in this case is we're going to cleave or break that hydrocarbon chain. Now this one, it happened to break it right in half. So you end up with 2 molecules with 6 carbons each. Now it turns out one of them usually ends up with a double bond and the other ends up with a single bond, but it doesn't always happen right in the middle. So you might do this and one of your chains might have 4 carbons. Well, if you started with 12 and one of your chains has 4, how many does the other have? Yeah, you're right, 8. So it doesn't necessarily have to be even, but we're going to take large molecule, break it into smaller ones, because the smaller ones we're going to find to be a little more useful in most of our applications. Not all. That could increase the cost of your jet fuel because we take jet fuel molecules and we make them into smaller molecules. It's all about supply and demand. Now, not only can we change the length of the hydrocarbon chains, we can also change the structure, or if it's a chain, or if it starts having branches. So looking down here at the bottom, this one is considered to be unbranched. That first one's unbranched. It's just a chain. It just has one carbon right after another. The second example has some branches. So there's one branch, there's another branch, and those branches, it turns out your engines like them a little bit better. It likes a branched molecule. Now, just as a little bit of review, let's see if we can name these 2 compounds at the bottom. Ooh, I'm mean to you. So this first compound, it has, it's just straight line. There's no branches on it. It has 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons all in a row. We would call that octane. 8 is oct. Ane refers to the fact that it's a hydrocarbon, meaning that hydrocarbon alkane, where there's only single bonds. Now, if we look at the second structure, we're going to look at the longest chain. So there's the longest chain. We have 1, 2, 3, 4, 2, 3, 4, 5, 6. It doesn't matter if you number left to right or right to left. The second carbon will always have the side chain. On the side chains, there's one carbon, that's a methyl group. Here's another methyl group. This would be 2, 5. There's 2 methyl groups, so we call it dimethyl. And there's 6 in the longest chain, so we call it hexane. 2,5-dimethylhexane. I know you're not an expert at naming, but that gave you a little bit of review. Well, let's see what happens when we have all these different compounds that come together for your fuel. So when you go to the gas station and buy fuel for your vehicle, that fuel that you buy is not just one compound. I never had even thought about what type of compounds you're putting into your vehicle when I was young. Never crossed my mind. But that gasoline that you buy is not just one chemical compound. It's a variety of different ones. And they have mixed all of these different links together to try to give you certain characteristics that you want in your fuel. So there's a mixture, over 100 different hydrocarbons, different lengths, different shapes, whatever the case might be. There are some trace contaminants. Now those trace contaminants, it's really hard to remove all of them. That's why there's some left in there. It gets too expensive to try to remove it all. But as that hydrocarbon burns, those contaminants are released into the atmosphere and can cause pollution issues. We also have some additives that are added. So we might add an octane booster, or what we're going to call an oxygenate, as we're going to hear about in a few minutes. So you could add ethanol or something like that. Sometimes they'll add like a detergent or a cleansing solution to try to keep your engine really clean. So that depends on the company you buy your gas from. So hydrocarbons, contaminants, and additives. We're looking for fuels that are going to burn really smoothly. And what they have found is that if you look at the individual compounds, the compounds that have more branches tend to do better in your engines. So let's see how they can describe that. All right, so way back when, years and years and years ago, when they were trying to describe the gasoline that they were using for vehicles, they wanted to give some indication of how good, we'll put that in quotes, good the fuel is. So one of the methods that they came up with is called an octane rating. Now, octane rating will sometimes mislead you. So this is what they were referring to. They started off by finding two types of hydrocarbons. The first hydrocarbon that they used was heptane. Okay, let's see if we can figure out what that is. Heptane. The prefix hept means 7, and ane means it's an alkane. It's just 7 carbons in a row. So 7 carbons in a row. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I'm not showing the hydrogens, but you know that each carbon likes 4 bonds. So if it's missing any of those bonds, it's going to have hydrogen surrounding it. Now, heptane does horrible as a fuel. The engines do not like heptane. So its octane rating, trying to write when it's up and down, it's a 0. Rating is a 0. Then they went and they found a fuel or a hydrocarbon that works really good in the engines at that point, and that was called 2,2,4-trimethylpentane. Oh, that's a good one. 2,2,4-trimethylpentane. Let's see if we can write this one out. So we have pentane. So ane means it's an alkane. It's only got single bonds. Pent has 5 carbon. 1, 2, 3, 4, 5. And then we have these prefixes. It says 2,2,4. So on the second carbon again, and on the 4th carbon, we have a methyl group. There's 3 methyl groups total. That's the tri. And methyl means it's 1 carbon. So on number 2, and on number 4, there's some individual carbon side chains on there. Now, 2,2,4-trimethylpentane, like I said, the engines really, really like. So it has an octane rating of 100. So we have from 0 to 100. Then what they did is they started mixing these two hydrocarbons. So in the example that's given to you, it's looking at an 87 octane. So they took 87% of the 2,2,4-trimethylpentane, yeah, it's fun to say, just say it over and over, and 13% of pentane, and they mixed it together. And how the engine responded to that fuel is how they determined the fuel has an 87 octane. So today, when you go to the pump and you choose the octane that's 87 octane, it's not just those 2 compounds, it's actually a bunch of other compounds and additives and contaminants and all that good stuff. But the engine responds the same as if the fuel would be 87% 2,2,4-trimethylpentane and 13% heptane. I know it's like just a really slight difference in how we explain that, but it's the engine's response to a fuel that would be similar to having a certain ratio of just those 2 hydrocarbons. Again, the fuel you buy today has a whole bunch of different ones, but it makes the engine respond the same as this other fuel would. Well, as you know, we always want to try to cut cost, and we want to try to make our product better. So we know that we could change the molecules to make it to where the engine likes those particular molecules better, but that is very expensive. So what they do instead is they have octane enhancers. So they add something to the octane to try to make it work just a little bit better. So here are a few of the different things that have been done over the years. Back in the day, they used to put lead in your fuel, and they used a special compound called tetraethyl lead. Let's see if we can figure out this compound. We have lead, Pb, and off of that lead, there's 4, that's tetra, ethyl groups, and ethyl means 2 carbons. So 2 carbons, 2 carbons, 2 carbons, 2 carbons. That's your tetraethyl lead. Again, I haven't included any of the hydrogens just to make it a little bit easier to see. And they found out that if they added a little bit of this tetraethyl lead, it would raise the octane rating by 10 to 15 points. That is a huge jump. But there were some issues. So it was good in that there was less knocking of the engines. The engines really liked this particular fuel, this particular additive they would add to the fuel. But anytime you have a lead compound, there's a certain amount of toxicity that's related to it, especially if it gets into your water source. So if there was ever a leak at a gas station, or you accidentally poured gasoline on the ground, that lead would get into the water sources, and that's bad. That's really, really bad. It also poisoned what's called a catalytic converter. Now, a catalytic converter, these came out in the mid to late 70s. So what they did is they said, okay, cars at this point they have too much pollution. So what we're going to do is we're going to change the cars so that they produce less pollution. And one of the ways they found to do this was to add at the very end of the exhaust system was to put a catalytic converter on there. And the catalytic converter has a variety of different metals, as palladium and platinum and all sorts of different things that act as catalyst. Remember, catalyst is something that allows a reaction to happen without being used up, and it allowed for these unburned hydrocarbons to go ahead and decompose, or it would make carbon dioxide instead of carbon monoxide. It just made the exhaust less polluting. So that's why you have catalytic converters on your car. Again, very simplistic explanation here. But here comes a big but. If you use leaded fuel, it would coat all those metals, and it would destroy the use of that catalytic converter. So you put this expensive piece on, and then you ruin it almost immediately. It is said that for leaded fuel, they needed less than 1 teaspoon of this tetraethyl lead per gallon. It would help raise the octane number by 10 to 15 points. But like I said, the leaded fuel would poison the catalytic converter. And they said it could poison it in less than, I'm trying to find it in my notes here, as little as 2 tanks of fuel. It would completely destroy the activity of the catalytic converter. So then what are you going to do? Well, what they did is they switched from leaded fuel. So when I was a kid, many years ago, I can still remember getting regular and unleaded. So regular had lead in it, unleaded, of course, did not. So they phased out the leaded fuel because it wasn't really great for the environment. But you still have this idea that you want to have as high of an octane rating as you can. So what else can you put in? What other additive can you use? So then they started looking at what are called oxygenates. Oxygenates include lots of oxygen in a compound to help increase combustion, because remember, to burn something you have to have oxygen. Well, one of the ones they used was MTBE. And MTBE stands for, again, let me get my correct slide here, methyl tert butyl ether. So it shows a little picture of it down here on the bottom. The colors represent the elements. So there's an oxygen right here, and then there's a bunch of carbons. So that oxygen would help promote the complete combustion of the hydrocarbons. But MTBE is an ether, and it turns out ethers are not good for groundwater. It would also leach into the soil and get into the water sources and cause a lot of issues. So MTBE was probably not the best thing. Today we use a lot of biofuels. Ethanol is a very common component to add. So ethanol is over here on the right, on the bottom. We have 2 carbons. The red is oxygen, the white is hydrogen. So 2 carbons, an oxygen, and a hydrogen. Is missing the other hydrogens that go on carbon. Again, we left them off just for simplicity's sake. So whether or not you approve with the use of ethanols, it is in a lot of our fuels. You will hear people talk about the good and the bad. There's a lot of debate over that, but it does add, or it does allow farmers to have a value-added agricultural product. So I'll leave the debate, and whether or not it decreases your fuel efficiency, that's for another day. So when you go to the pump, to the gas station to fill up your vehicle, you have a choice of different octane ratings. So there's some of the different octane ratings that you might see. So 87, 89, 93, very, very common. You can actually have over 100 octane. You might say, how can that be? It just means that the engine has a better response than it did for a 2,2,4 trimethylpentane. But most commonly, that's like racing fuel that you'll see that for. But most common at gas stations, 87 to 93 are very, very common. So then at the very top of that number, you might see this right here. Oh, I don't know if you can see it very good. It says R plus M over 2. My pen's skipping out again. There we go. R plus M over 2 method. That's supposed to be a 2. There we go. What that refers to is that depending on how you drive, you're going to get different fuel efficiencies. R stands for research. That means you have the gas pedal on the floor. You're driving very aggressively. The M stands for motoring. So that means you're just kind of cruising along the interstate. You know, you don't have a lot of starts and stops. You're not trying to go super fast. You're just happy as can be. Well, generally you get better gas mileage if you do that. The research method is a little bit harder on your vehicle. And what we do is we average those two numbers together to get an idea of what that octane rating could be. This particular fuel, you'll see that it says it also contains up to 10% ethanol. Ethanol is going to be used as your oxygenate to add that oxygen to promote complete combustion of that fuel. It's also considered to be an octane enhancer by increasing your octane rating. Again, there can be other additives that are being added to those fuels. All right, so what is used to help unreacted hydrocarbon fuel molecules combust into products? We have the catalytic cracking, catalytic reforming, catalytic converter, or a spark plug. On this one, the catalytic cracking takes a big molecule, breaks it into small pieces. So it's not actually used to help unreacted hydrocarbon fuel molecules react. No, we're actually changing the molecule structure to allow it to be more efficient. Catalytic reforming, we actually reform the molecule. We add more branches to make it a better fuel. But they're not helping unreacted hydrocarbon compounds go ahead and combust. That's what the catalytic converter does. It's in the exhaust system and it helps aid the completion of those combustion reactions. A spark plug starts that reaction. It allows the start of burning those hydrocarbons, but to actually react let me restate that. to help the unreacted hydrocarbon fuel molecules. That's going to be your catalytic converter.